All right, so I'm just having trouble getting getting online here, but oh, maybe did it finally come up here? Cetane number. Let's see what happened. No, it's still. I don't know. I was able to get to some other prominent sites, but anyway, if it comes up, great. If not, so the next bit, engine tests, and like Brian says here, only if you love the technical minutia. So this is the amount of soot produced. So here's diesel with more soot. Here's 100% biodiesel with less. So here you go. BD blends have lower emissions in total hydrocarbons such as carbon monoxide and particulate matter. Biodiesel blends have higher NOx emissions in general. Up to 5% do not create any engine problems, like fouling or corrosion. And then table 310 for contaminant effects on engine. This is on page 77. So he does recommend that you go ahead and pop out to page 77. Yeah, so those are all listed. I'm not going to go over them. I'll just let you look at them on your own. No connection. That's okay. Okay for now. Okay, so some of the challenges. Change in emissions. So the newer engines have more emission issues than do the older ones, the pre-1998. And I don't know if that's just because of the fuel injection versus the carburation, but that probably is part of it. Yeah, and so here's what's happening. You've got the oxygen molecule itself in the fuel is combining with the nitrogen in the air. There's just more oxygen around, and making it that much more likely for NOx to form. More expensive, less energy. And warranty issues. Those are all the things we just covered at the very end of the chapter. So that's it for chapter 3. We went through the reading assignment. We saw the notes. I think I launched the discussion. Here's an example problem. Let's just take a peek at that. Yeah, we should do this problem. Is that going to wreck your groove, Jonathan, if we go right till 2 o'clock?
Oh, no.
Is that okay? Okay.
As long as you need to.
Well, okay. All right, let's just take a look. Good to do a problem. Okay. So standard transesterification reaction. This is page 45 in the text. Let's go back and review what that is. Yeah, so that's the one we looked at with the 3 alcohols involved. However, since the reaction is at equilibrium, goes both ways, researchers have found by adding extra alcohol, it drives it further to completion. So let's see, we've got 100 pounds. Let's see if I can get both these screens on the page at the same time. Switch them this way. It won't let me move it off the page. It's okay. All right, so here we go. So we've got a vat, 100 lbs, 100 pounds of triglycerides. Chemical formula, so these are pretty, oh, does it say 1,000? Oh, gosh, thanks. So half a ton about. And so this is a big old molecule, C55, H98O6. How many pounds of methanol is needed for a 90% conversion yield? So we're looking at CH3OH. So let's go to, excuse me, figure 3.2 in the chapter, figure 3.2. Okay, so this is a good little figure. So it's just showing the more of the alcohol we put in, the greater yield we can get. So to get figure 3.2 on page 47. And so the way to do that, you just go in and put a square across there. Go to 90% is near the top, and that takes us to a yeah, it's right at that little knee. Molar ratio of 8 to 1. So we need 8 of these guys to 1 of those to get to 90%. So how many moles of triglyceride do we have? This is the tri. Okay, so obviously we have to go from mass to moles, so we can do the stoichiometry. Okay. So if you remember, carbon has a molecular weight of 12, hydrogen has a molecular weight of 1, and oxygen has a molecular weight of 16. So the so we'll first do the acid methanol. First do the acids. So we've got no, I'm sorry. Let's first do the triglyceride. So basically, just going to multiply 12. So that's the molecular weight of carbon times 55. That's how many there are. Plus 1, that's the molecular weight of hydrogen, times 98, that's how many there are of those, plus 16, that's the molecular weight of oxygen, times 6, because there are 6 of those, equals 854. Now this is a terminology I'm not 100% comfortable with or familiar with. So when I look at this, I see that this 854, that's going to be grams per mole. And again, 1 mole is 6.23 times 10 to the 23rd molecules. So if you had 1 mole of hydrogen, it would weigh 1 gram. Since this is such a large, large molecule, it's just bigger, 854 times larger. So in this case, you're going to have, instead of 854 grams per mole, that's the equivalent of 854 pounds per, and this is just another number. It's just called the pound mole. And let me think about that for a second. And a pound mole is just going to be the number of moles required to make a pound of material. So it's still a number. It's how many moles there are to make a pound of that material. In the previous case, we know that 854 grams is in 1 mole. So a pound mole is however many moles there are in a pound. I wish I could draw a picture of that, but we'll see about doing that next week. Okay. So now we just need to know, then we need to get to the methanol. So eight of those. Figure 3.2, we need to know, therefore, 1.7. Okay, so now we just need to know how many pound moles we have. So let's do that next. So X is to 1,000 as 1 pound mole is to 854 pounds, because we know we were starting out with the pounds. So X equals 1,000 lb times 1 lb mole over 854 pounds. So let's do that little bit of math. So 1,000 divided by 854 equals 1.17 pound moles of the triglyceride, and that's where that comes in. So times 8, so 1.17 times 8 equals 9.37 pound moles of methanol. Okay, and then basically we're just doing that same stoichiometry we did in reverse. We know that the molecular weight of the, and I won't write this out, we know that the molecular weight of the methanol is 32 pound moles, so significantly less. When we multiply the 9.3, and I will go ahead and do this one, finish this off. What's that? So we'll just go ahead and say, so the 9.37 pound moles times 32 pounds per pound mole equals 299.8 pounds of the methanol, CH3OH. And that's to get 90% yield of the biofuel. Okay, so I mean, and really, that's about all there is to the majority of the problems in this class. And so just to get a better feel of what the mole is, I know I haven't really talked about that much, but let's just look at it this way. Let's just do hydrogen versus carbon. So if I have 1 mole of hydrogen, that's 6.23 times 10 to the 23rd hydrogen atoms. And let's just say I start drawing them all. There they are. I'm going to be tapping a long time because there's a lot of them, but there they are. There's that many hydrogen atoms sitting right there. I could condense it, squish it, liquefy it, whatever, put it on a scale.
Solidify it.
You know, maybe you can't solidify hydrogen. I think you might be right about that.
Better holy grail if you did.
You can try.
They say you can do it in anode cathode electroplated.
Oh, yeah?
They say it's been done in Russia, yes. But that is the holy grail if you can solidify hydrogen.
I wonder what that would even look
'Cause
like.
that's like the ultimate fuel.
So what, you'd have to get to absolute zero for it to happen, or what? You have to be really super cold.
Yeah, and I've heard that of helium. In fact, there's well, I'll take one side tour if we might here.
No, there are people that are actually trying to crush it together in little tiny vices.
Really?
Yeah.
That's wild. I like to come in here and change the temperature. Yeah, there's a little temperature slider on this guy.
Oh, sweet.
Yeah, so if you start cooking the periodic table,
Nice.
yeah, I mean, if you take it cold, everything gets black, which is solid.
Huh?
You take it up here, it starts getting red, which is gas.
Nice.
I love it. You keep going and check out carbon. Like, there's still tantalum, tungsten, rhenium, and
Yeah.
osmium at the bottom. Melted, 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 melted.
Carbon, no way, bud.
Yeah, so we're 3,700 Kelvin. Carbon finally melts at, like, I don't know, just shy of 38. And yeah, now let's go the other way.
A lot faster than our other stuff.
Yeah. If we go this way, you can see all these things are still gases at 719 Kelvin. Now we're down, there's mercury. You can see mercury and galenium, phosphorus are liquid at 347. Bromine comes in.
0.
That's, yeah, so chlorine is still a liquid at 223. Now pretty much everything's solid at 99 Kelvin. Neon still a gas, helium. So this is, I mean, so at zero,
Hydrogen.
well, yeah, that's when you said you can't solidify hydrogen. I've heard that about helium.
There you go, but you-
I just hadn't heard it about hydrogen. So if I tweak this up, this is telling me that helium liquefies at 4 Kelvin. That sounds right. And that hydrogen, yeah, I don't know, I just don't know much about it. Says that hydrogen can be solid at, well, 16 Kelvin. I mean, that'd be one energetic ice cube, or hydrogen cube. Anyway, to get back to this discussion, what I really wanted to show is that 1 mole, or 10 to the 26 times 6.23 times 10 to the 23rd hydrogen atoms, not molecules, which is H2, but atoms, has a mass of 1 gram. And the same thing, 1 mole of carbon, so just take that same 6.23 times 10 to the 23rd, and again, that's just the number, you're just going to count them up, all these carbons. Since there are 12 protons, since there are 6 protons and 12 neutrons in that carbon nucleus, the thing's going to have a mass of 12 grams.
Where'd you get those numbers from again?
Well, 6.23 times 10 to the 23rd, this is Avogadro's number. Avogadro.
Avocado.
And basically, it was Avogadro that sort of tied the atomic world, the molecular world, with the world we live in. It's just, okay, keep counting, 10 to the 23rd, and now you've got a gram.
Pretty big, man.
Yeah. So a pound mole, I just want to look up the, yeah, let's look up the pound mole really quick here.
The Moltox, 1 pound Moltox. Keystone Pest Solutions.
Moltox.
Let's get it.
Listen to that, man.
Kill some moles.
Keystone Pest Solutions, the Moltox 2.
Different kind of mole, huh?
I don't know, something's going on with Wikipedia here.
Wikipedia's going handshake between viruses. It burns when it pees.
Yeah.
Okay, so there we go. What's a mole? A certain number of molecules. There it is. Oh, you know, I forgot the 0. It's 6.023 times 10 to the 23rd particles. That's a gram.
Very nice.
And that's just what we call a mole, but they're saying, no, this is a gram mole. Or a kilogram mole. Well, there we go. 1,000. So it'll have 1,000 times more particles. A pound mole is 6.032. It's Avogadro's number times 424. Where's that?
Therefore larger than a gram mole.
So there must be that many grams in a pound. Is that right?
I don't know. That's-
Grams to pounds. Let's do
That's
that.
what the derivative is now.
Let's go 1 pound. Let's go a stone to a gram. There.
It is.
Yeah. 454. That's 424.
Huh.
Close, not quite. Yeah, I need to dig into that a little bit more. It's not 100% clear to me.
Where's the shovel?
Volta.
Good dig into the vault talks.
Null talks. Okay, well, the important thing to remember though on this problem is that we did use consistent units. Okay, that's all I got. We'll, oh, no, I don't. I got one more thing. One more thing. I'm going to launch the week 4. Now I'm going to launch week 4 on Thursday, the week 4 discussion board. So anyway, guys, here's the thing. There's one student, I'm not going to embarrass him by stating his name publicly, but you got to finish up that week 1 and week 2 so we can share the answers with the rest of the class and move on. So, all right, we'll see you on Thursday.